Hey team, I'm Maddie. Welcome to Science Side Up. And today I'm actually pretty excited for today's reaction video. But first, the life updates. Okay. Currently still pregnant. We're 2 weeks away from my due date at the time of filming this. So but it is 9 o'clock in the morning and it's not a million degrees outside. So I'm in my office. I've got the fan blowing. I'm sorry if you can hear that. I'm going to try to edit that out in post, but we'll have to see. Trying to get a couple more videos recorded before baby makes their appearance. And we'll just have to go from there. So you guys are super cool. I'm super glad you all are here. And okay, so today's video, what are we talking about? I really wanted to title this something obnoxiously dramatic, like in which Maddie makes this one particular guy on Reddit really mad by reading graphs. But that would be a long title, though rather accurate, because sometimes I get on Reddit and I get on r/climateskeptics and I respond to arguments and articles and things that are posted there. And I made this one particular guy real mad. So I thought we could enjoy this together and look at some climate change denialism stuff and react to it and read some more graphs and maybe continue to make this one particular guy upset. Okay, so let me show you the post I decided to comment on. And this is the type of post I generally decide to comment on, where it's like I can reasonably assume, infinite things. I can reasonably assume that at least someone on, that's not where we want to start. We want to start here. Okay. Sorry. Okay, here we go. I can reasonably assume that at least someone looking at this is genuinely confused, or it's reasonable for me to assume honest actors who don't have the specialized knowledge to understand kind of what's being presented to them. So this is the graph that was presented with this SpongeBob-y title of We're Doomed. And so what this is global average temperature anomalies from 1979 to sometime in 2022. So basically to present. Okay, yeah, there, to June 2022. So, okay, so I was reading some of the comments. By the way, my Reddit name is really, really clever. It's just, hi, I'm Maddie, right? So this is me. You'll see me around here. Okay. So, this person looks like an upward trend on a relatively short time span. Yes, absolutely. And then there's this, this is OP here. This Redditor is the one who I made mad. So he's from 1988 to 2022, there's an upward trend, right? So we go, hey, let's look, right, 1988 to 2022. I mean, there is, if you're going to do a linear regression onto that data, you don't go peak to peak. Anyway, so here we go. I'm looking for a comment. And this person is correct. People with no experience looking at data shouldn't. Well, I'm not going to go that far. just recognize, like, because if I want to learn about something, I want to go look at data. Um, uh, but if it's in a new field, then I need to understand how to read that. So here's the thing. I was reading through some of the comments on this, and basically it seemed to me that a lot of folks who are looking at this thought were unclear about what this zero line meant. It seems to me that they thought it represented uh, like what temperature should be, or an overall average of like all data we have from the US, right? So maybe I need to back up a second. So this is a temperature anomaly. So what that means is that we took the global average temperature and then subtracted off an average value. And so then what we're plotting here instead of actual temperature is how different temperature is from that average. So that's what we're plotting. And so let's just jump down to like my initial comment. Okay. Oh my gosh, where's my comment? In here somewhere. Maybe. Yeah, okay, sorry. So here's my initial comment. I like that I have a -1 on, I have a -1 upvotes. So I'm just like, hi, I'm a PhD candidate in meteorology. And the main thing I want to point out is that this is a plot of temperature anomalies, which means whoever made the plot subtracted off the average value. So the zero line represents an average. By reading some of the comments, I think there's a misconception on what that average is. Many people seem to think that it's an all-time average, but that isn't the case. So what average did they use? The standard in atmospheric science is to use a 30-year mean, and the most common one used is 1981 to 2010. So these anomalies are most likely all relative to the average value of those years. So that's where I was going to leave it. And then OP replies, the zero line represents an average. Can you provide the absolute number for this graph? Note it's satellite tropospheric data, not ground stations. And shouldn't we be able to get the number by simply using the US standard atmosphere? Okay, so the answer to both of those questions is no. Can I provide the absolute number for that graph? I didn't make the graph, so I didn't post the graph. So unless I know how the graph was made, I don't know exactly what the average is, right? As a number. Okay, and then shouldn't we be able to get the number, that average number, simply by using the US standard atmosphere? So a standard atmosphere is a really useful tool. It's saying that's like, hey, this would be a really boring atmosphere if, say, everywhere on planet Earth, mean sea level pressure was exactly 1,000 millibars, and temperature, pressure, and density are all going to change with height based just on the adiabatic lapse rate. That's a useful tool. If you've watched any of the Weather 101 stuff, we know that's like, okay, this is what a really boring, basic, simple atmosphere, simple Earth atmosphere would look like, but this is what's really happening. It gives us understanding what a standard atmosphere or what like normal would be, and then comparing what's actually happening to that standard atmosphere helps us kind of get a sense of what's going on. So it's a useful tool, but it's inappropriate to apply it here. And the reason is US standard atmosphere, everything in that would be a derived quantity, not a measured quantity. So what do I mean by that? Derived meaning I did some math and came up with this, right? So math likes to work in perfect worlds. And you generally, and so, yeah, so we derive this derive this standard atmosphere from like first principles. That's all well and good, but it's not representing the real atmosphere. And the reason that a derived quantity is inappropriate in this situation is because, specifically, he says right here, satellite tropospheric data is what is plotted. So that satellite is the important word there, because that means this is measured data. So it would be super inappropriate to compare measured data to derived data. What we should do is compare satellite data to satellite data, right? So what you're going to do to make this graph is what you're going to do to make this graph is find that average value from the satellite data and then compare satellite data to the average value measured in the satellite data, right? So we're comparing apples to apples. We're not introducing anything new here. And that's how you would do that. That would be the most appropriate way to do that. All right. So OP says this. I get another -1 on my comment here. So then I say, I don't know exactly how the graph was made. So since I don't know exactly how the graph was made, no. I'm guessing that they're using either a monthly or seasonal global average for that time period, but I don't know what that's supposed to be specific data set they pulled the data from. But you wouldn't use the same number for the average for December as you would July. Additionally, the temperature value would specifically be measured, not empirically derived. So that's what I'm trying to say. So one, I'm also trying to say that it's not a single number, because this is, you want to subtract because the average temperature in July is very different than the average temperature in December, even when you're looking at a global average, right? So we generally are going to use like a monthly mean value versus, or maybe even a seasonal mean. So seasonal mean would be a 3-month average. And why do I think that they're using either a monthly or a seasonal average? Well, take a look at the graph. Okay, so we're looking at years here. All right, so this would be 91, 92, 93, 94. Sorry if this is kind of small. And I was looking at this on my phone, so I couldn't quite tell how many data points we had per year. But it's more than one, right? So every time we see a little kink, a little sharp edge in the graph, that is a data point. And so we're going to be taking, say, let's just go start with 1982. We're going to be taking, it ends up being a monthly, is what the data ends up being, but I didn't know that at the time of writing my comment. So in 1982, we would take the average global temperature based off this satellite data for January of 1982 and subtract off of that the climatological average for January, right? And then we would go to February and then plot that point on this graph. And then we would go to February and we would take, okay, what was 1982's February global average temperature, and we'll subtract from that the climatological average, and so on and so forth. So there's not a single number, and using a standard atmosphere is incorrect. Again, because it's incorrect might be the wrong word there. It's not the best thing we can do. It's not kind of best practice. I really hope, let me check something. Sorry, I didn't mean to have infinite. There we go. Okay. I wanted to make sure you guys were actually seeing what I'm seeing as I'm derping around. Okay. So then he gives me a link of where the data comes from, and I went and I read that briefly. So they're using a 91 to 2020 average, which is certainly appropriate. It's slightly less common than using the 81 to 2010, but people are shifting over to using that. So they used that 1991 to 2020 average, which isn't uncommon in the field, And it is a monthly average. So if that isn't clear, they took a global average for each month over 30 years and then subtract the correct value, January average from January for a single year, and so on to make the graph. So what the graph is showing is, say, how much colder 1979 was from that 1991 to 2020 average, or how much warmer 2018 was from that average. Hope that helps. And he's like, hope that helps. And he's like, not really. I've asked for a single number, and I thought I've explained really clearly that there's not a single number, and if it can be derived from the standard atmosphere. And I also thought up here, I made it clear that using the standard atmosphere is inappropriate. But I could have been like clearer about like, no, you can't do that. And then he gets a little snarky. This is where I said I think he gets mad. You know the standard atmosphere? Yes, I do know the standard atmosphere, and I'm not going to like, oh no, what's the word? I'm not going to I'm just not gonna engage with this like kind of disrespectful behavior, right? And so here I try to be very, very clear. There isn't a single number, and it cannot be derived from the standard atmosphere. There are 12 numbers, one for each month of the year. And then he's like, I've asked you for a single number that is used in the above graph. That's your answer? Meteorology, you say, eh? Right? So he's all snarky. He's like asking me for a thing that doesn't exist based off the graph that he showed. And I'm like, my guy, you don't know how this is made. And so I just stopped responding because like we're getting away. I felt like at this point in this conversation, I could no longer assume good faith actor, right? And you know, I get it. Maybe I'm like naive for thinking that was something I could assume from the beginning. But that's kind of like a level of I don't know why this word is so hard for me to pronounce. Naivety. I always want to say like nativity, and this is probably my like Oklahoma accent coming out. But anyway, uh, yeah. But anyway, you guys know what I mean. Like, I understand that it's naive to assume people posting on r/climateskeptics are like good faith actors who just have been misinformed. But like, I feel better about humanity if I assume that. So I choose to, despite evidence to the contrary. I think I commented somewhere else on this same thread. So while we're here, let's just have some fun. And let's see if I can control F. But that's me. Because I think I'm in like 2 comment threads. Oh, okay, here we go. Yeah, so under one of the things under my original post was somebody, this logical progressive person says, don't forget another good reason to graph anomalies is that a 0.1 degree change makes an alarmingly big bump on an anomaly graph, but a 0.1 degree change makes an unimpressive blip on an absolute scale graph. So I actually disagree with this. Like, it depends on your y-axis, you know? But that's fine. And so this is so this is why climate alarm science uses anomaly graph. You can't scare people with a graph going from 15 Celsius to 15.1 Celsius. So I tried to kind of ignore the vitriol in that and just replied that using anomalies is actually really standard in the field, whether you're communicating with the general public or other scientists. So what I was trying to say with that sentence is that, like, presumably in the climate scientists are an evil cabal worldview, like when it's behind closed doors and we're talking to each other, we wouldn't need to use alarm tactics. right? If we're all in on it, you know. Anyway, so that's what I'm trying to point out is that like no, we just use anomalies because they're convenient and they communicate more information than absolute temperature. Um, and that's what I'm explaining here. So it's so that we can see at a glance how the data compares to normal. For example, back in July, the high where I live in the Midwest, I didn't want to say Oklahoma on here, but I don't know why. Now I'm showing you guys. You all know I live in Oklahoma. And in parts of England, we're consistently over 100 degrees Fahrenheit. But that's not unheard of for my region and record setting for England. Looking at anomalies helps us understand when the weather or climate is behaving abnormally. So my point there was that the anomaly in England would be much greater than the temperature anomaly in Oklahoma for the same absolute temperature. Anyway, and then, but this person jumps on to my using anomalies as standard in the field. And it's like, because it obscures the true insignificance of our so-called climate change. And I'm like, oh, okay, so I'm not going to engage with this guy anymore. So I guess I made two particular guys on Reddit upset. Anyway, so that was kind of fun for me. Honestly, that gave me a chuckle. But while I was going through this, I thought it might be fun. I pulled up a couple other choice r/climateskeptics things posted by our friends that I annoyed. Okay, so let's maybe go through a couple more. How does that sound? I hope that sounds like fun for you. Sounds like fun for me. Okay. Okay, this was what I wanted to look at. This was posted by the second guy. I assume a guy. Yeah. So this is climate activists are dancing for joy. No global warming for 7 years, 11 months now. So let's take a look at this graph. So let's continue to be snark on Reddit by reading graphs correctly. I'm excited. So this comes from What's Up With That, which has some just terrible climate stuff. Anyway, so let's grab this graph. Okay, so so this is 2015. This 2015 starts here, so maybe we're getting 2014. No. Last little bit of 2014. But here's 2015 to 2022. And hey, look, we have a trend of plus 0 degrees Celsius. Oh, sorry, that is the linear data. Okay, so this line is the linear regression of this particular window. So, one, these are oh no, guys, as the indefatigable, apparently I can't English, Eric Worrell reported here a couple weeks back, the forces of darkness are becoming concerned at the lengthening of the new pause. I didn't know I was part of the forces of darkness, but I want a t-shirt that says that now. Yeah. Okay. So, this is, I think this graph is made in the same way that other one was, but let's take a look. Is there a link? There is a link. Ooh, but that's not a hyperlink. That's upsetting. Okay. I want to know how this graph is made and what we're actually plotting, right? Because we're clearly plotting temperature anomalies. Okay. But we're not told exactly what 0 is. Uh, but I'm gonna bet actually that it is. I'm going to bet that it is that 91 to 2020 average. And let's just take a little peek. So we're going to compare it to that last graph we looked at. So 26, the highest value is at 2016, and that's the only time we get above a 0.6, and that's like February 2016. Okay, so yeah, that looks So I think what somewhere here. I think this graph is effectively this graph, but zoomed in, starting at 2015 and going forward. And that's kind of what would make sense to me. Or it's at least very close. It might not be the exact same data set, but turns out in the robustness of climate science, you can use different data sets and get the same overall picture and very close to the same exact numbers. Anywho, I'm enjoying being a force of darkness, though. Okay, so so why might the trend in this particular subset of the overall data be zero, and why does that not actually matter? Great question. One, this is only a 7-year period. For us to consider something to be climatologically interesting, it needs to show up on a 30-year trend, right? So big difference, right, between weather and climate. Two, if we're thinking about these as anomalies, right? Because that's what we're plotting here. Hey, if we had subtracted off that 81 to 2010 mean, we might see a different trend here. But we subtracted off 91 to 2020, right? And so we would expect a lot of these values, which fall right in that average, right? So 2020 is here, 2015 is down here. So one note that even though these years are included, up to here, are included in our climatological mean, we're still really consistently falling up. Like, we only fall below zero like twice. And then, oh my gosh, look, 2021 had a cold, an slightly abnormally cold winter. Anyhow, so these types of variations are certainly expected in climatology, right? So this idea that 7 years worth of data represents a significant climatological trend is actually inherently just false. Again, we want to see that trend over 30 years for it to be something we're going to think about seriously in a climatological sense, because there are plenty of things that are called like decadal patterns. So El Nino, La Nina cycles are one example. That's kind of an easy one to throw out there. So if you have several strong La Nina years in a 10-year period, or several strong La Nina events in a 10-year period, then that might make you behave cooler than the climatological trend for those few years. So turns out atmosphere really complicated, and it has periodicity across multiple time scales. So there are known mechanisms that affect kind of average temperatures in a over like 5 to 10 years. There's known effects that are going to affect it over periods of like 50 years. known effects that are going to affect it over 1,000 years, known effects that are going to affect the atmosphere over 60,000 years. Right. Climate, natural climate variability happens on multiple time scales. It turns out the natural variability is much easier to capture than man-made variability. If we're thinking of just the science, or like climate models and things like that. So a 7-year trend, or a lack of a trend over 7 years, doesn't actually tell us like anything. Now it would be interesting to know from a science perspective, like just a pure science perspective. Ooh, cool. Why is this happening? Right? We would love to be able to know exactly why this is happening, because that's going to help us forecast climate in the future. Right? Climate is very difficult to forecast. In fact, your weather forecast is like only good out to 7 days. If anybody is trying to forecast something greater than 7 days out, be very sus. Okay, so here's this. So I, as a member of the forces of darkness, I am not concerned with the new pause. Anyway, I'm not concerned about it. And all right, let's move on. So let's pop to StreamYard and do this. How long have I been going? About half an hour. Okay. One of these guys also posted some stuff on Arctic sea ice, so I thought that would be very fun to look at, because Arctic sea ice is my jam. That's what I think about all day, every day, when I'm not decorating a nursery or being really anxious, especially about to be responsible for a very tiny, helpless person. So that's going to be exciting. No, we're really, really excited for baby. I am really, really ready to not be pregnant, is where I'm at in my life. Hope you guys are doing well. Okay. So let's go ahead and go back to sharing my screen. Hello, our infinite regression there. Okay, surplus Arctic ice, July 2022. That sounds like that's up my alley. So let's take a look. Okay, so let's look at the graph and then let's look at the comments. That's probably all we'll do today, but I don't know, this greenhouse effect on the moon? No, the moon doesn't have an atmosphere. It's too small. Okay, cool. So this is Arctic sea ice. Cool. So this is 30th of July, 2016. Cool. Cool. Oh, shoot. Sorry, this is an animation. Maybe we can let it play. And the animation shows Arctic ice extents. So this is Arctic sea ice extent on the end of July, starting with 2007. Okay. There's 2022. Okay, so 2007, 2010, 2013, 2016, 2019, 2020, 2021, 2022. Oh gosh, how are we oriented? Sorry, there's Greenland. There's Svalbard. Okay. This should be, watch over here by Svalbard for this year. 2020, 2021, 2022. We're really far retreated. Okay. So this is the animation. By the way, guys, this animation I think shows pretty well why I have a thesis, why I get to write my dissertation on Arctic sea ice. Notice how from year to year there's a lot of variability in Arctic sea ice extent, not just kind of in the total area, but also in where like, so yeah, like look over here. This is like the Barents Sea. This is the northern coast of Alaska. So like watch this area and see how very different the sea ice extent is just in that part of the Arctic from year to year. So there's a lot of this spatial regional variability from year to year, even as like overall total sea ice extent, just the total area, is showing a declining trend. Kind of where you lose ice every year or where you lose the ice from year to year in the summer when you get melt changes, and we don't strictly know why. And that's like the big question my dissertation is not looking at addressing, but looking at like that's the big question, and then I narrow that down to my specific topic, right? But like what you're looking at here is the problem. Now, record minimum sea ice extent is still 2012. And let's pull up NSIDC. Sea ice extent NSIDC. Chartic. Okay. Chartic interactive sea ice graph. I think this is where I want to be. Yeah. Oh, yes. Okay. So this is sea ice extent at the end. This is sea ice extent going back. We can look at any year all the way back to 1979. By the way, why does so much data become available in 1979? Why does so many graphs start at that year? That's the first year satellite data is reliably available, so it helps us study the whole world. So this is the satellite era. Okay, so this thick gray line is the median. This is from 1981 to 2020. Anything, and then like the shading is like quintile ranges. So what you can think of that is anything that's in a shaded region is sort of normal, climatologically normal. Record minimum was 2012. That's this red dashed line. So we can see the behavior across the whole year of that 2012 record minimum. And then this year, 2022, is being shown in blue. So notice that, hey, look at this. We are above that record minimum, but we're certainly below what we consider average. So we are outside of these quintile ranges, outside of those shaded regions, trending downward towards our seasonal minimum, which is at the end of September. But we are unlikely this year to break the record. So I don't think we're going to break the record this year. We kind of don't have the right. You have to have certain. What we think, right, is you need to have certain conditions early in the summer and then other conditions late in the summer. And we didn't meet those like early conditions. Before 2012, I think the record minimum was in 2007. So let's put that up there too. Yeah. So look at that. We're even above. Right now, we have more sea ice in the Arctic than we did in 2007. 2007 was a really weird year. And then let's toss one more up there. Let's just toss 2018 up there for funsies. And right now we're pretty close to the 2018 value, right? So again, we're seeing an overall downward trend in sea ice, especially September minimum sea ice extent, but there is interannual variability. So, you know, the minimum is still 2012. Yeah, so it's, you know, we consistently get less summer sea ice now than we did in between 1981 and 2010, but how much we get at the end of the summer varies because it's complicated and I have a job. Anyway, okay. So here's the article then. Was it? Okay, yeah. So it was an article, but I clicked on this animation. And so let's go back. So we watched the animation, we kind of understand the problem. So let's read some of this. It shows Arctic sea ice extent at the end of July for a few years. And we see that there is a lot of regional variability. July average Arctic sea ice extents. This is kind of odd to me. We don't really, in the Arctic community, we don't talk about July extents very much. Usually we talk about like September and March, because September is when we're going to get the minimum, and March is when you're going to get the maximum. So a lot can happen between July and September. So this graph is comparing July month ice extents from 2007 to 2022. Notice that like in 2020, by the end of July, we had less ice than we did in 2012. But I'm going to take off. Okay, so now we just have 2022 and 2012. Let's put 2020 on there. But lo and behold, right, the line, we crossed beams again, and we end up with more sea ice at the end of 2020 than we did at the end of 2012. So I don't know why we're looking at July here. That's not really a good year. Okay. So July Arctic ice extents. Cool. Oh, that's silly. They're not showing 2012. You should show 2012 in this, because that's that record year. That's very important. Okay. The melting pattern during July 22 remained above average all month. But this was, we have a surplus of, but the area is more. That doesn't, that using that word surplus is also meh. I don't know what you mean by that. Because like, here's another thing to point out. 2022, look, here's my maximum value, right? So if we want to talk about an ice surplus, ice had a surplus of ice in 2012, in March compared to this year. So that word surplus to me implies like, oh, look, ice is growing in the summer or something like that. Like it's trying to, like that's not the language I would use to describe it if I was trying to communicate as clearly as possible. But, here we are. I'm not sure that's the goal of this article here. Okay. So I think we can be done with this. Let's take a look at some of these comments. So surplus Arctic ice, you're capturing interannual variability of Arctic sea ice. Turns out, team, that's a thing. Doesn't mean the overall trend isn't sharply downwards. The author refers to an interesting article from 2006, whose conclusion is that the results presented in the study support conclusions of this author, who found evidence of persistent ice retreat since the second half of the 19th century. Wavelet analysis of the time series presented in this work gives evidence that this decreasing trend is being superimposed on multi-decadal oscillations in ice edge positions in the Nordic seas. The analysis suggests the presence of a 60 to 80 year variability, and also of 3 decadal oscillations in ice extent. We associate the multi-decadal mode with the so-called low-frequency oscillation found in the Arctic climate, possibly associated with the North Atlantic thermohaline circulation variability. So, okay. things we have learned since 2006, and something that's really important that's happened since 2006 is this change in March extent. So basically, what we think is happening is that uh, we're is that ice thickness has dramatically plummeted. Um, so it used to be that most sea ice in the Arctic is what's called multi-year ice. So it's ice that doesn't freeze and melt in the period of a year. It stays there all year, and then next year more ice grows on top. Well, it actually grows up from the bottom, but so we get more ice and more ice and more ice. So now we have ice that's really, 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 really thick. So this is why we see this, how narrow our normal range is in like winter, and here's my like March maximums compared to down here, right? Down to my minimum. So it used to be that most of what melted to give us our um, uh, minimum September sea ice extent was all this thin first year ice, leaving the thick multi-year ice alone. But over time, we were thinning out that multi-year ice. So if you're just taking a picture from the top, all you're seeing is area, right? You're not seeing thickness. So, and sea ice extent is a measure of area, just area. So, so over time though, we're thinning that multi-year ice, and now we're starting to melt it. This kind of kick starts in about 2007. So I bring that up because the article that they're quoting from here is from 2006. So I'm actually a little, there's a little grain of salt there, and I would need to read the full paper to really like get this. But anyway, oh, this is fun. The European Alps show similar patterns. Ever heard of the Iceman? Yeah, what about him? What's the connection? What do you think? You did some research, I guess. Hey, turns out snow and ice on land is very different than ice that is frozen seawater. Those behave differently and respond to different things. The physics is different. So you can't, that's apples and oranges. We really can't compare. Okay, and that's all. That is all we've got there. Okay. Well, hey team. We've been chatting for a little while. Thanks for hanging out. I'm getting hungry, so I'm gonna go inside and get some breakfast, and it's already starting to heat up. So I'm gonna try to get a few more of these recorded and baked before baby makes her arrival. And yeah, so if you stuck it all the way to the end, thank you so much. I'm glad you're here. YouTuber chill stuff that I should remember to do. Please like, subscribe, all that jazz, share the video out. And that helps the channel grow, that kind of thing. If you desire to and are able to financially support the channel, you can leave a super thanks down below in the comments section, or in the description to this video, you'll see a link to my Buy Me a Coffee fund. That's always appreciated. Otherwise, you can, I don't know, watch an ad and not skip it. That's the main way I make revenue. And you guys are super cool, and thanks for hanging out with me while I reviewed how I made this one particular guy very mad on Reddit by reading graphs. Okay, I'll see you guys later. Bye, team.